we're back to the Inside Scoop Emerald Planet. Here again, your host, Dr. Sam.
Hello and welcome to the Emerald Planet as we look for those 1,000 best practices, the best of the best going on around the globe in 144 different countries. And also we're looking for those experts that are looking at the notion of climate change, the impact of climate, and of course populations, food security, all these other issues as we go to a planet of some 9 billion people by 2050. So as we look at all this, how do we actually predict and know what may be happening? As many people know, it's very difficult to predict climate, the weather, and of course the negative impacts that are happening around the globe as more and more human activity. And we have a gentleman sitting right beside me who's published a book called Mathematics and Climate. This is Dr. Hans P. Engler. He is the co-author, also co-director of what's called Mathematics and Climate Research Network. And he's a professor of mathematics in the Department of Mathematics and Statistics at Georgetown University. You're a busy guy.
Thank you, Sam. Thank you for having me here. Here's our book. This is our book, published, and it's a textbook for students. You can buy it on Amazon. A small correction, I'm not a co-director of MCRN. I'm an ordinary member there.
That's fantastic. Yes. That's fantastic. Anyway, looking at the work that you're doing, you're at Georgetown University, and then you help write this book. Now, you have a very heavy teaching load. I know that from looking at your website. So publishing, writing, being a full-time, faculty member, how do you balance that, and what's the intersect between mathematics and climate?
Well, balancing it, I consider making new material, new challenges in mathematics and broadly sciences that are applicable to the fate of society and decisions we all make. That's part of my core mission as a university educator. Mm-hmm. At Georgetown, we are in the District of Columbia, the most important city in the world, as everybody likes to say, and we all, being locals, agree, of course. We have the chance to educate future leaders and future people who will shape, and further foster the direction that the world will take. So, mathematics and climate is one such challenge, or more broadly, environmental change, broad global change. And so, here's a chance for us, we thought, to make this connection more precise. And I have to say, it was also an opportunity to bring a new angle towards teaching mathematics, because there are lots of examples from climate which are of interest to students and accessible to them.
Yeah, and I looked through your textbook, and it's very detailed. You have many charts, maps, mathematical formula, and all that in there. So what really motivated you to spend this amount of time to publish a textbook, which is now actually being adopted all across the globe? This first came essentially out of the formation of MCRN, and Hans came to me and said, "Why don't you teach a course about this? I have some ideas." So now this is Dr. Hans Kapper,
right?
Yes, okay.
The other Hans.
Make sure we keep our Hanses all
yes.
organized here.
So then looking around, I found there's no textbook. And course notes and notes from students, observations from students developed into this textbook. It was as much a learning experience for us trying to assemble and organize all this material as it was a writing experience. And learning, of course, is part of the fun.
Mm-hmm. And also, too, this is very important for the students to realize that professors are actively involved in doing the research and actually getting this out, because again, this is being adopted in the United Kingdom and India and many other countries. So it's important to the students to realize this is actually going on.
It is much easier, I find, to communicate to students what these questions are, because in a sense the newspaper headlines are written for us. News clips, reports are being put in front of them almost daily. So they're well motivated, and then it's not such a big step anymore to get them interested into the mathematical treatment of these questions.
Well, as you're saying, I think this is a very astute observation that the media really is getting the message out there. You know, there are a few deniers that there's no climate change and other things, but it's so few that it's you know, almost laughable because, you know, the science is overwhelming in what we're doing. So anyway, looking at what's the synergy as far as mathematics and climate science?
In a sense, mathematics, as Hans Kapper already said, it's the language of all science and therefore also of climate science. With the advent of the satellite age in particular, since the 1980s, so much data is coming our way that you cannot really do anything with it without a serious mathematical, algorithmic, statistical kind of treatment. And of course, in a sense, computers are the laboratories that climate scientists use these days. Whenever they come up with different scenarios for different CO2 emission scenarios, for example, it's always a computational experiment. It cannot be a planet-wide experiment. It's impossible. So
because it's just too huge. The amount of data is just too huge to process.
The amount of data is too huge, and also, if you wish to, for example, have a climate model that takes into account that there are, let's say, Rocky Mountains somewhere, the place where Ken is sitting, you need a supercomputer that can resolve all the fine detail. You cannot do it on a PC. You can make a climate model on a PC. It will have about 6 different boxes, as they say, 6 different places in the US, and that's it. The entire country covered by like 6 squares. So you cannot even see rivers or mountains in them.
Yeah, that's just absolutely amazing. What are some of the examples of where you're actually applying mathematics to climate studies and really looking seriously at climate change and the impacts that it's having? Because, you know, people are saying, you know, humankind is really having a huge impact as far as climate as today. And I assume through your formulae, but you're actually being able to prove some of that, or at least lead us towards understanding of what's actually going on.
One should first, well, the main application of a mathematical backbone, as it were, is when they come up with different scenarios for, let's say, the temperature development through the end of the century, depending on different emission scenarios, then there's always computation behind it, which is based on mathematical formulation. That said, the uncertainties are much bigger than even a numerical weather prediction. So the uncertainties, the range at which a prediction is made is not as good as even, for example, the weather forecast for a week from now. But you can always show that's, for example, without CO2 emissions, we would not have what we're seeing right now. That is uncontroversial, and that is a mathematical computational argument. And then there are many, many smaller scale regional questions that people are interested in. For example, one big question is, can we predict a future El Nino event? The current one that leads to floods in South America, droughts in India, wetter West Coast, a milder winter in Canada, all these things. If one could predict it at least a year in advance, which is outside of our range right now, then one would have a much better chance of preparing, adapting, and making the event less impactful.
Looking at climate change, this is one of the things that most people cannot really dismiss, is that it's becoming more violent in many ways. The flooding, the tsunamis that are going on. I mean, all these things are happening almost simultaneously across the globe. Huge droughts in diverse places like Brazil, Australia, western part of the United States, China, India, and all that. So as you're doing these mathematical formulae, how do you fit that in? Because you're saying the data is so huge, you have to have the supercomputer to do all this, but at the same time, the reality is that we're having these extreme weather patterns. How do you fit that together so it makes sense not only to the students, but also to the greater public as far as what is really happening?
There is a mathematical theory of extreme values, and it was originally developed for things like floods, hydrological extremes. That said, when you have an extreme weather event, let's say a hurricane season with a very large number of Category 5 hurricanes, then you cannot say that this is due to climate change. But what you can say is something the same as when an athlete, a baseball hitter, hits all of a sudden twice as many home runs in a season than he did before. You cannot say this particular home run was due to the steroid use, but the overall pattern, the change in the pattern, is due to the steroid use. Mm-hmm. And that's sort of the main, that's a similar approach that one also uses when one attributes changes in the frequency of extreme weather phenomena to climate change.
So can you say that due to climate change, you have now weather patterns that are like being on steroids?
Right. You could, for example, say you might have Hurricane Sandy, probably something like that, more frequently in the future. Mm-hmm. Maybe no longer every 100 years, but every 20 years, which means you have to rebuild your infrastructure, of course, and prepare for it.
Yeah, it's just like people put in flood walls 20, 30 years ago, and they said, well, this is for 100-year floods or 500-year floods. Now they're finding that, well, now we've had 3 100-year floods, but within a decade.
Within a decade. So now it's no longer a 100-year flood. Mm-hmm. It's now a 10-year flood, maybe.
And again, it goes back to this huge investment as far as infrastructure is concerned. Looking at the outcomes as far as COP21, mm-hmm. the United Nations Conference on Climate Change that was held in Paris, France, how is mathematics being applied to that, to all these different criteria that the various nations, all the nations around the globe, bought into and signed off on as far as addressing severe climate change?
I was not at the COP21. A lot of the preparation material that was used to look at different scenarios was done with climate models. Then looking forward, there are decisions which are made where one has to make a choice between this or that particular approach to mitigating climate change. And mathematical decision methods, optimization methods play a role. Mm-hmm. More broadly, mathematics can play a role in talking to decision makers, explaining to them the variability of the predictions, the possible outcomes, and even more broadly, since we are educators, and this is a multi-decade effort, I'm thinking of the students who are in my class right now as the ones who will make decisions in future decades and maybe by 2050 be the senior leaders, hopefully, and influence things. And I can prepare them for that a little bit.
Yeah, and this is saying about what you're doing as far as being at Georgetown University, where you have a very internationalized student body. Well, anyway, thank you for being with us.
Thank you.
This is Dr. Hansby Engler. He is the co-author of the textbook Mathematics and Climate, working at Georgetown University as we create the Emerald Planet.